Hi there, this is Dr. Dell, and this is a video on the subject of real numbers. It's an introductory video, and real numbers can be viewed from either a theoretical or a practical viewpoint, and we're going to look at it from a practical viewpoint, the way that I think everybody should probably learn it in the beginning. And then for those of you that might be interested in the philosophy or the theory behind mathematics, I'll probably do a video or two on the theory of real numbers. But first, before one does that, one should learn about it from a practical viewpoint. Now, actually, you already know a lot about real numbers. A real number is simply a number that you can write, for example, 2.13, or rather 213.75. 213.75 is an example of a real number. You could also have fractions, which could be real numbers. For example, 2/3, which could be written as 0.667. You could make it 0.6666666 as far as you wanted to, and at some point you'd probably want to stop. Now, what makes real numbers, the reason they're called real numbers, is because if you take a straight line, you can actually assign every point on that line to a real number and vice versa. Now, as you know, this is kitchen table math, and so my drawings are not going to be particularly pretty, but the idea is to get is to understand the concept behind it. So typically, for the real number line, you would take a point and you would arbitrarily call it 0, or it's an arbitrary point you call 0. Then you would take another point. Usually you go to the right and you call that 1, and that establishes what amounts to a ruler or a scale. And from that point on, every real number has its location on the line. So, for example, you move an equal space to the right, and that would be the counting number 2. Another equal space, the counting number 3, and then 4, and then so on indefinitely. The real number line, theoretically, extends forever. If you move to the left an equal space, you go to -1, the first negative number, and then if you go to another space to the left, you have -2, -3. And as you can see, basically the negative numbers are kind of like a mirror image of the positive numbers. If you think of a mirror centered at 0. Now, the whole idea behind numbers is to find their location on the real number line. And we use, to express real numbers, we use something that our ancestors invented called a base 10 positional system. And quite frankly, this was a wonderful invention. Probably we wouldn't be able to do near as much with numbers if somebody had invented this or something equivalent to it. And let's make sure now that you understand this. I think this is a review. Most of you already have some mathematical training, and so I don't expect that this is going to be new information. But this is an example of a real number, 745.385. Now, what this means, based on the base 10 positional system, is that this 7 stands for 700. So you have 7 times 100, or 700. Then, based on its position, you add to this 40, because 4 times 10. You add to that 5, because that's 5 is the first position left of the decimal point. So the first position is multiplied by 1, the second position by 10, the third position by 100. And if we had more digits, there would be 1,000, 10,000, 100,000, and so forth. And then when you go to the right of the decimal point, you have 3/10 for the first digit. The second digit, because of its position, is 0.08. That would be 8/100ths. The third digit would be 0.005. And so that's how the number breaks down in the positional base 10 decimal system. Now, 3/10 could also be written as 3/10. 8/100ths could be written as 8/100. 5,000ths could be written as 5/1,000, and so forth. So this is what the meaning of this number is. And I hope that that is simply a review for you. The position of the decimal point determines the size of the number, of course. For example, you could have 87 and several zeros for a number, and then the decimal point. And we usually use commas. The first 3 zeros represent thousands. The next 3 then get you up to 1,000,000. And this would then be 870 million. It's a pretty large number. But you could also have a decimal point here and have a bunch of zeros and an 8-7. And now we don't usually put in commas, but you could. And so now we have tenths, hundredths, thousandths, 10,000ths, 100,000ths. This is 8 1/millionths, and this is 7 10/millionths. So you might express this then as 87, let's see, I think it would be 87 millionths. In any event, this is how the positional number system works. Now the point also I might point out is that no matter what the real number is, it will fit somewhere on the real line. And you have to choose your scale so that you can put your number in. If you were going to put in 745, you'd have to go way, way out on the line, so you might choose a different scale. You might put the 1 back here so that this would be 100, this would be 200, and so forth. And we'll worry about those kind of things when we get into practical problems. Now, something that you need to think about when you think about numbers is the number of significant digits. And so I've already prepared this. Let's start at the top. We have this number 345.29. Now, a question you always ask yourself is how many of those digits are significant? Does that 9 really mean something? Does the 2 mean something? And that all depends on how you're measuring your numbers. And generally speaking, some of these digits probably don't have much significance. Let's take, for example, suppose you were counting the number of people in a stadium, and the number was 37,892. Well, are you really sure that 2 is significant? In other words, would you bet your life that it was exactly this many, or might it be 37,891 or 895? As a matter of fact, maybe it's 37,906. After all, the difference between 37,892 and 37,906 is only 8 plus 6 is only 14. So as a matter of fact, what you might do is decide that you only really know this to the nearest thousand, and 38,000 might be a better way to express this number, where the 3 and the 8 are significant, but the other digits really aren't. They're just placeholders. Depends on how much accuracy that you really think you can measure things by. So for example, if 38,000 was how you stated the attendance, that would imply that it could be anywhere from 37,500 up to 38,500. If this digit 8 is significant, then these digits could vary up and down by, say, half that amount, so by half 1,000 is 500. Now, it may turn out that you decide that this digit isn't really significant, and you might want to round it off to one significant digit and say the attendance was about 40,000. The rule of thumb here is to use your common sense. That's really the basic thing that you want to do. Now, we're going to use calculators in our example. So let's start off with this calculator, and I clear the register. And let's take 1 divided by 7, or 1/7. And if you can read that, if you have a high-definition version of this video, you should be able to read it. It's 0.142857143. So I wrote that down here, 0.142857143. Now, if you were actually measuring something, do you think that these later digits would actually have any significance? Do you think you could measure something to that degree of precision? Well, there are situations in science where, as a matter of fact, you can, but that would be very, very rare. And in ordinary, everyday practical math, probably if you had 0.143, that would be all the significant digits that would matter. Chances are you couldn't really measure any closer than that. And indeed, 0.14 might even be adequate for most situations.